Imagine yourself aboard the International Space Station, floating effortlessly above our planet, watching Earth spin slowly below. Amidst the hum of machines and the silence of space, a small device silently ticks away, the atomic clock. It is not just any clock, but a marvel of modern science that keeps time with astounding precision. Yet, how does time flow for this clock in microgravity, far from Earth's surface? Does time behave the same way in the weightlessness of space as it does here on Earth? Today, we explore this fascinating question, diving into how atomic clocks behave in microgravity, what experiments have revealed, and why understanding time in space is crucial for science and technology. To grasp this topic fully, we need to understand what atomic clocks are and why they are so special. Unlike ordinary clocks that rely on mechanical parts or quartz crystals, atomic clocks measure time based on the vibrations of atoms themselves, nature's most stable timekeepers. For example, a cesium atom vibrates at about 9,192,631,570 cycles per second, and counting these vibrations defines the second in the International System of Units. This extraordinary precision allows atomic clocks to lose or gain only about 1 second every millions of years, making them indispensable for technologies like GPS, telecommunications, and fundamental physics research. Now, why does microgravity, essentially the condition of very weak gravity experienced in orbit, matter for these clocks? It turns out, gravity affects time itself. This is no ordinary statement, but a profound insight from Einstein's theory of general relativity, which tells us that gravity warps space-time, causing clocks to tick at different rates depending on their position in a gravitational field. Clocks closer to massive objects, like Earth's surface, tick more slowly compared to clocks located farther away, such as those on satellites orbiting high above. This phenomenon is called gravitational time dilation. In microgravity conditions, like those on the International Space Station orbiting approximately 400 kilometers above Earth, the gravitational field is weaker than on the surface. So, the atomic clocks aboard the ISS experience time differently compared to those on the ground. But how much differently? And what about the motion of the space station itself? Here we encounter another relativistic effect, special relativity's time dilation, where clocks moving at high speeds tick slower than stationary ones. The ISS travels at about 28,000 kilometers per hour, around 7.66 kilometers per second, which is incredibly fast compared to anything on Earth, adding complexity to the overall behavior of time on board. When we combine these two relativistic effects, the gravitational time dilation, making clocks run faster in weaker gravity, and the velocity time dilation making clocks run slower due to high speed, the net effect on the ISS clocks is subtle but measurable. Experimental results and detailed calculations show that the high velocity dominates, causing clocks on the ISS to tick slightly slower than clocks on the ground. This means astronauts living in orbit technically age a tiny bit slower than people on Earth. A fascinating example of time's relativity in action. Scientists have rigorously tested these predictions using highly accurate atomic clocks sent into space. For instance, the NASA Atomic Clock Ensemble in-space mission and similar projects involve placing atomic clocks in orbit to monitor their behavior in microgravity. These experiments confirm that time dilation effects align with Einstein's theories with astonishing precision. Such experiments not only deepen our understanding of physics, but also improve practical applications, such as synchronizing satellite systems and preparing for future interplanetary missions. Let's look closer at how these clocks function in microgravity environments. An atomic clock works by using microwaves to stimulate transitions between energy levels in atoms, and the frequency of these transitions determines the ticking rate. On Earth, gravitational fields can cause minute shifts in these energy levels, known as gravitational redshift, which in turn slightly alter the clock's frequency. In microgravity, these shifts are reduced, potentially improving the clock's stability. However, the physical environment in space presents challenges. Temperature fluctuations, radiation exposure, and mechanical vibrations can influence clock performance, requiring careful engineering and shielding. To understand the nuances, consider the history of precision timekeeping in space. Early experiments during the Apollo missions placed atomic clocks on the Moon, where gravity is about 1/6 of Earth's. Scientists observed the expected time dilation effects consistent with general relativity. More recently, experiments aboard the ISS and dedicated satellites have advanced the frontier of precision and understanding. These experiments have paved the way for next-generation clocks, such as optical lattice clocks and quantum clocks, which promise even greater precision by exploiting quantum mechanics and ultra-cold atoms. Why is this understanding of atomic clocks in microgravity so important beyond theoretical physics? One key area is global navigation satellite systems, including GPS, GLONASS, Galileo, and Beidou. These systems depend on extremely accurate time synchronization among satellites to determine precise locations on Earth. Without correcting for relativistic effects, positioning errors would accumulate rapidly, resulting in navigational inaccuracies of kilometers each day. In essence, understanding and compensating for time behavior in microgravity directly impact everyday activities like driving, air travel, and even banking systems relying on precise timestamps. Beyond navigation, precision timing in microgravity has applications in earth science, fundamental physics tests, and future space exploration. Atomic clocks in space can detect tiny variations in Earth's gravitational field, aiding geophysical studies such as monitoring sea level rise or tectonic activity. They also provide platforms for testing physical constants and searching for possible new physics beyond Einstein's theories. Moreover, for future missions to the Moon, Mars, and beyond, having reliable and ultra-precise clocks that behave predictably in varying gravitational fields is essential for navigation, communication, and scientific experiments. The fascinating interplay of gravity, velocity, and atomic physics in microgravity environments also invites philosophical reflection. Time, which seems universal and absolute in daily experience, reveals itself as fluid and relative, shaped by motion and gravity. This challenges our intuitive understanding and underscores the profound beauty and subtlety of the universe's laws. In summary, atomic clocks in microgravity are not just precision instruments, but gateways to understanding time itself. They confirm Einstein's theories in the harsh environment of space, enable technologies we rely on daily, and open new frontiers for science and exploration. As we continue to improve clock technology and extend our reach into the cosmos, these clocks will remain at the heart of our quest to navigate, measure, and comprehend the universe.